now. If you need a tornadogenesis expert, these are two folks you can definitely go to. So they're going to share some of their knowledge with us here. So with that, please take it away, Aaron.
All right. Well, hopefully everybody can see the opening slide here, Spring Seasonal Symposium.
Looks good on our end, Aaron.
All right, awesome. Well, hopefully the audio stays up. I do have a tour group of 100 second graders wandering around my office, so probably not as cute as Patrick's child, but you may hear some kids screaming in the background, so I apologize if it gets noisy. But anyway, do appreciate the opportunity to present as part of the seasonal symposium here. For those that attended last week, this is a complete clone, so but if you see something new, don't be afraid to ask questions at the end. So as I already mentioned, John Stopcotty's joining me on this, and really the two of us are the main authors for this training. So with that, we'll get started. All right, so just a brief reminder for those that may have forgotten, as the TWIP is composed of the following 8 individuals across Central Region, including yours truly. So feel free to contact any of us if you have questions or comments. So for FY19, we had 3 main areas of focus for training deliverables. Obviously, a leading item was to develop a Supercell-based Tornadogenesis series that emulates the previous release QLCS Mesovortex and Landspout tornado-based training. And I'm going to spend most of the time this morning discussing the background on this topic. And then in addition to that, we also wanted to expand the QLCS-based Mesovortex training with inclusion of new modules on competence builders and nudgers. And then finally, we wanted to reiterate the awareness of human bias in warning decision-making. So one of the key questions many folks seem to always ponder is, why do they need supercell-based tornadogenesis training? Because after all, supercells are easy, right? Well, it was apparent at the onset of the TWIP that, at least in the area of supercell-based tornado warnings, the integration and application of the latest peer-reviewed research has lagged. So instead, there have been many attempts to kind of reinvent the wheel with legacy techniques in hope it will somehow improve our performance, yet the opposite has really occurred. And so specifically, improving TOR warning false alarms has been kind of a long-standing goal, yet without applying new conceptual models and radar-based interrogation, those numbers have really changed little beyond just a few percentage points. However, after the 2011 tornado events, where concerns over false alarms were raised, and we experienced, though, an abrupt drop in both the probability of detection and lead time to well below our national GIPR goals, such as the 13-minute lead time. And those numbers don't change much when just looking at only our region. So while a variety of reasons can exist for stats to change over time, including increased reporting of weak tornadoes through social media, and even simple year-to-year variability, this same signal is seen in stronger tornadoes, which we know emanate almost exclusively from supercells, as shown by the study from Harold Brooks back in 2016. And so specifically here, the red line implies that there is an increasing number of strong to violent tornadoes where TOR warnings are not being issued until after the tornado is reported to be ongoing. So the last I checked, that's still called a missed event. Now in this same time period, we've seen an increase in guidance inferring that a raising of rotational velocity thresholds was the key to improving performance. However, this was provided really without a full understanding of temporal and spatial limitations of scan-to-scan rotational velocity couplet values as a prognostic tool for genesis. By the way, I'm getting a lot of background noise. Are you guys hearing that too? I'll take that as a no. Okay, fair enough. All right, so unfortunately, whether it's right or wrong, we continue to see some groups in the weather enterprise using our performance issues against us. Hence, we can't just keep reinventing the wheel with legacy techniques, as something has to change. So a core issue was noted very early on in that too many folks are either directly or indirectly applying outdated conceptual models of tornadogenesis. And some of that's done, again, through indirect use of these continued use of radar interrogation methods based on these outdated conceptual models. So, for example, the historical rationalization with looking at rotational couplet magnitude trends were based largely on the dynamic pipe effect for genesis. The main assumption is that the circulation aloft was thought to be a precursor signal based on the belief that rotation strengthens at progressively lower heights until a funnel makes contact with the surface. Unfortunately, this is not observed, as older studies suggesting this genesis process, especially those using 88D obs, have been found to be an artifact of temporal and spatial resolution limits of the radar used and the inability of the human eye to discern rotation in the absence of debris. So in contrast to this dynamic pipe effect, we're seeing this growing number of studies that are finding a bottom-up process for tornadogenesis that exists potentially for several minutes before growing upward very rapidly. And so this is important because it implies that this is occurring at levels that the 88D cannot sample or resolve before appearing maybe as a spike in rotational couplet strength after the tornado is ongoing. And it also exposes a serious R2O disconnect, as this has been known via field projects for years. So this results in several impacts, including the reality that legacy radar interrogation methods are insufficient. And so to illustrate this, we'll start with a process that I think is all too common in tornado warning decision-making by applying legacy reflectivity pendant and velocity couplet analysis, but as a prognostic tool. So we're going to back up to about 13 minutes before a potential tornado, as we have to use the tools available at this time if we're going to issue a tornado warning to meet our national goal. Now, obviously, very similar looking supercells don't all produce tornadoes. So you might be thinking that all we need is the rotational velocity magnitude of maybe any low-level couplet and we'll be good to go, right? So we introduce the half-degree SRM and immediately notice there's no defined couplet in any of the cases. So maybe we aim for number 3 as the highest threat since it has the best looking shear, number 2 a little weaker, and maybe number 1 is the least likely. So for those that have been through the training, you already know that this is completely misleading. Because this type of analysis doesn't really tell you much about the potential for tornadogenesis, because in this case, number 1 produced an EF4 tornado starting 13 minutes after this time period. Number 2 produced an EF3 tornado, and our best looking option, if we're just to go with the half-degree couplet analysis, was a non-tornadic supercell. So hence inclusion of half-degree couplet analysis is not the answer if we have any hope on improving. So a key impact from this core issue is that many warning mets don't really understand the role of the low-level mesocyclone in tornadogenesis. You know, research tells us that one of the primary tasks of the meso is actually to increase stretching via dynamic lift of near-surface baroclinically generated vorticity. It's not the same vortex as the tornado. So what we're seeing with the 8AD is, in most cases, not the tornado. So this results in an important point that too much evidence exists now that shows that diagnostic values of low-level mesocyclone magnitude are not reliable prognostic tornadogenesis tools. So as the event shown to the right illustrates, the mesocyclone circulation, shown as the black and gray shading, doesn't change much until genesis already occurred. Plus, as has been shown by research, a strong low-level mesocyclone doesn't solely determine tornadogenesis, as non-tornadic and tornadic supercells alike can both have strong low-level rotation. Additionally, through field projects and high-resolution simulations, it has been shown that genesis is much more complex than an oversimplified process of just evaluating the current mesocyclone intensity. With it stated, there are still some proper uses of rotational velocity couplet magnitude, such as message refinement with things like IBW tags in follow-up statements of existing warnings. Of course, these warnings should be deemed necessary prior to this point through use of other more prognostic interrogation methods. So this need for other interrogation methods brings us back to the reality that, fortunately, in a lot of forecasters' analysis process, that method for predicting supercell tornadogenesis has not substantially advanced beyond techniques that originated from the 1970s, which, again, a lot of it was based on the dynamic pipe process of genesis, which we know is outdated. So this recent trend towards raising of velocity couplet magnitude thresholds without infusing new analysis is likely one of the causes of degraded performance, especially with stronger tornadoes. So because of that, we have to start using things like dual pole, as it does open a whole plethora of new interrogation techniques that can use the hydrometeor character to infer both kinematic and thermodynamic properties at the storm scale. And these create new prognostic tools for anticipating genesis. And I hate to state the obvious here, but a lot of people don't get the difference here. We're not talking about a tornado debris signature, as it would be a little hard to call a TDS a prognostic tornadogenesis tool when obviously it's suggesting an ongoing tornado or one that already occurred and is now dissipated. So the TWIP training on supercell-based tornadogenesis is designed to kind of help solve these challenges by initially explaining the latest research findings and impacts on conceptual models. Further, with this background, it explains how legacy techniques will not provide the level of prognostic information necessary to anticipate when things like the low-level mesocyclone intensity would increase, rather than just reacting to diagnostic values. And finally, an in-depth discussion and examples of new radar interrogation methods is provided that can help infer kinematic and thermodynamic storm scale processes that, again, influence tornadogenesis. So just going to give you kind of a quick overview of what's built into these modules here for the Supercell Tornadogenesis series. The overall focus is on these four main areas, although with overlap between categories. The main goal, though, here is to expand your radar toolbox beyond using only legacy interrogation techniques. And this isn't about taking anything away, but more about proper use of existing methods and application of new interrogation processes. Plus, it should be noted that nothing radar-wise is bulletproof, as there are strengths and limitations to the existing and new interrogation methods that must be understood in decision-making. So the first series, this dives into the processes that help generate near-ground rotation and associated interrogation methods that can help infer this with the 88D. And so this includes understanding the role a low-level mesocyclone plays in tornadogenesis, along with a discussion essentially of what we're actually seeing with the 88D, and is also contrasted with what we're not seeing. And so this details some misconceptions of what, at least most people, or I should say most, what many people believe the 88D is resolving. And so this leads to an emphasis to anticipate changes rather than reacting to diagnostic values by bridging the gap with new conceptual model understanding and interrogation methods. And so this includes the introduction of dual pole signatures, such as the ZDR arc, which you can see here, because this can qualitatively infer changes in storm scale SRH due to its connection with low-level size sorting and the associated mean low-level storm relative wind. Of course, similar to any radar data, as I've kind of already mentioned, there are horizon limitations that reduce the range from the RDA where features are resolvable, but non-uniform beam filling can significantly reduce capability with dual pole to identify features such as the ZD arc beyond a certain range. So, for example, in order to ensure, say, the top of the half-degree beam is well below the frozen and mixed phase regions, in an environment with low freezing heights will substantially reduce the range from the RDA where dual pole features are identifiable. Otherwise, if you go beyond that range, you're going to be left with a product such as ZDR that shows nothing, as kind of illustrated in the images to the right, despite there may be active ongoing size sorting. Additionally, LP supercells, they can also create problems, as the overall lack of available hydrometeors makes it hard to discern any dual pole features despite favorable size sorting and associated shear profile. So the next modules in the series builds off the previous discussion on use of dual pole for feature identification, but details essentially a more refined process for qualitatively inferring storm scale SRH. And specifically, these modules elaborate how the introduction of hail, which there's a surprise, supercells can produce hail, can influence the relationship between the orientation of the ZDR gradient and the mean low-level storm relative wind and associated SRH. So to counter the hail issues, these modules discuss identification and use of what's called the KDP foot to better infer where smaller, more spherical drops are sorted by the mean low-level storm relative wind. And so this permits a method that combines the approximate centroids of the regions of enhanced ZDR and KDP to create a separation vector that we compare to storm motion. And so the orientation angle of this vector relative to the storm motion is critical, because something closer to being parallel infers mostly a crosswise dominant shear with reduced potential for intensification of the low-level meso. In contrast, something where you're starting at larger angles. Here I'm showing 90 degrees for pure streamwise, but really you start talking about angles of 70 degrees or up, 130, 140 degrees. These high angle environments qualitatively infer higher SRH, and of course, increased potential for low-level meso-intensification. And so several examples are provided, including tornadic cases within minutes of genesis that reveal little to no rotational couplet at the half degree, shown in the upper right here, but we have a high separation vector angle that qualitatively infers high storm scale SRH. Although not shown here, you can see that the low-level meso in that 3,000 to 6,000 foot layer does ramp up pretty fast. In contrast, we have non-tornadic cases that do have well-defined rotational couplet at half degree, but as you can see, a minimal separation vector angle that qualitatively infers little, if any, storm scale SRH. So the next category digs into how hydrometeor character inferred from dual pole variables is critical in assessing downdraft buoyancy, especially when it comes to knowing when to not issue a tornado warning. And so this training discusses tools that can assist with kind of the Goldilocks issue, as shown by Paul Markowski, where partial thermodynamic characteristics either help or inhibit tornadogenesis, regardless of the strength of the mesocyclone. Further, it's detailed how environments with strong negative buoyancy inhibiting genesis have a common dual pole base signature, indicating the presence of wet melting hail. So to aid in identification of environments where hail and or a rain hail mix is suggestive of very negatively buoyant downdraft, this conceptual model is discussed that can be directly applied to dual pole features identified on the 88D. So this includes, obviously, application examples of how Supercell illustrated these features, indicating a non-tornadic supercell, despite evidence, again, of a rotational couplet. So speaking of rotational couplets, this next training digs into more of the topics kind of discussed today, but more in depth with applicability limitations with diagnostic rotational velocity couplet analysis. So to fully understand kind of the long established practice of using couplets as prognostic tools for tornadogenesis, we go into a brief historical background, including associated connection to conceptual models that are now outdated. And this discussion is then moved forward to more recent research, illustrating how fine-scale mobile radar observations and storm-scale numeric weather prediction have revealed flaws in those earlier conceptual models and associated interrogation techniques still in use today. So you can see here for the same supercell, what you're seeing from the Dow data on the right, obviously is showing features and timing that you just cannot resolve with the 88D. So as discussed earlier, the radar interrogation methods built off these concepts are explained to be insufficient as prognostic tools. Hence, strengths and limitations of rotational couplet interrogation is discussed, including proper application. And so this includes methods that use low-level mesocyclone placement relative to downdraft boundaries as a better prognostic tool for anticipating genesis than just magnitude. And so finally, the last series, still in development. John and I are going to work with our partners in the research community. However, this training looks into a velocity-based feature called the Storm Relative Velocity Enhancement, or SRVE for short. And so I'll just give you kind of a quick preview of what this module detail. And specifically, we know from research that parcels feeding directly into the region under the low-level mesocyclone, which I got outlined here with the black oval, that those parcels are tilted and stretched to become the tornado, but they also emanate from the forward flank region. So this feature has been noted in previous research, including the velocity feature, but its relevance to tornadogenesis is just now being understood. And so to illustrate this, we use examples such as the Roselle, Kansas EF4 tornado from a few years back. And so this low-level SRVE feature emanates again from the forward flank region and is a strong indication of the bare clinically generated vorticity feeding into the region below the low-level meso that can ultimately becomes the tornado. Again, placement and magnitude are extremely important here because when dealing with hail-dominant storms, you may have some features that are not lining up. So that is a summary for the supercell-based tornadogenesis series, but also want to detail some of the new modules coming in the QLCS Mesovortex training series. So another one of the main goals of the TWIP was to detail the primary factors in the QLCS Mesovortex warning system, as this ultimately aids in creating a more science-based and consistent process for these type of tornadoes. So in FY18, hopefully everybody's gone through these, but we developed a training series on step 1 of this process via use of the 3 ingredients method for identifying areas of a QLCS favorable for mesovortex genesis. This includes application examples showing increased probability of a tornado. Now, we do briefly introduce step 2 within this training series. It uses confidence builders and nudgers to help identify increased risk of tornado development, but we really wanted to provide greater detail via additional modules on these features in order to assist the warning meteorologist with step 3 of this process, where you obviously issue an appropriate warning based on these signals. Of course, the final step is drawing an effective polygon for this tornado risk. So work is underway in adding these modules that will provide more detail, again, on the use of confidence builders and nudgers, including several examples. Additional modules detailing step 4 will be forthcoming down the line as well. So the final area of focus for the TWIP in FY19 was on furthering awareness of human bias in decision making. And so the reality, even in 2019, is that we still suffer from inconsistent warning decision making, not only from one office or region to the next due to things like office cultural differences, but within each office there are obviously varying levels of experience, warning philosophies, different radar interpretation skills, and of course just overall human bias. So the ultimate goal is to eliminate as much as possible these factors to create a more consistent and scientific process. Now, much of the information detailed today with supercells and QLCS tornadoes should improve the science and interrogation issues, but we also have several human factors and associated bias to deal with. So the TWIP has several recommendations for hopefully mitigating these negative human factors in warning environments. This includes hitting directly at making staff more comfortable and receptive to second opinions, also to be more introspective with understanding tendencies and limits of yourself and others. And so we are proposing for this spring into summer to introduce a short survey to warning meteorologists on the effect of human bias on these actual tornado warning decisions in 2019. So that's a pretty quick update on the 3 things from the Central Region TWIP training for FY19. As a reminder, you can find TWIP material on the Google and VLab sites mentioned below. So not sure if I have time for any questions, but I guess I can take them at this time or at the end of this.